All right, let's set the stage for a futuristic showdown. In one corner, you've got the classical artificial intelligence that pretty much powers our entire world today. And in the other corner, the challenger, a brand new kind of AI, one that runs on the absolutely mind-bending rules of quantum mechanics. So the big question is, where's the tipping point? We're going to jump into a fascinating new study that put them head-to-head in a high-stakes medical challenge, all to find out exactly when this futuristic quantum brain actually outsmarts the AI we know and use every day.
So yeah, could a quantum computer be our next doctor? Let's dive right into this fascinating experiment that really puts that question to the test, pitting these two types of intelligence against each other in a challenge where the stakes, well, they couldn't be higher.
You see, the core question here isn't about some far-off theoretical promise anymore. We're past that. It's about finding real, practical, in-your-hands advantages. Where does quantum actually win?
And this quote right here, this is the exact question the researchers were trying to answer. Nailing this down is absolutely critical for figuring out where we should be focusing our time, our money, and our brain power as we build the next generation of computing.
Now, to get an answer, the scientists couldn't just, boot up a quantum computer and hope for the best. They needed a way to give it a head start. So they came up with this really clever framework called NN2QC. Think of it like a special translator that takes all the knowledge from a classical AI that's already been trained, all its memories and experiences, and converts it into a language a quantum computer can actually understand. So here's how this translator works step by step. First, you extract all the learned patterns from the classical AI. Then, you scale them down, using a specific math function to shrink those huge classical values to a size that can fit into the super delicate quantum world. Third, you initialize the quantum circuit with this translated knowledge, kind of like giving it a starter brain. And finally, you fine-tune it, basically letting the quantum AI take that knowledge and run with it, learning and improving all on its own.
And what you get at the end of all this is something called a variational quantum circuit. Don't let the name scare you. Just think of it as a hybrid system that gets the best of both worlds. You've got a quantum processor doing the heavy lifting, but it's being guided and coached by a classical computer. It's basically a quantum brain with a classical coach. Okay, so the quantum AI is now armed with all of the classical AI's wisdom. It was time for the main event, the competition. The researchers set up a whole series of challenges to see which one would really come out on top. And the battlegrounds were really diverse. They had a few synthetic puzzles, abstract things like telling apart crescent moons and nested circles, but then they threw in one incredibly important, real-world task, diagnosing breast cancer from 569 real patient samples. This is where it gets real. And this is where things get really interesting, because what happened next wasn't just a simple win or loss. The results revealed this fascinating pattern about where each type of AI truly, genuinely shines. So on the easiest task, a problem where the data could basically be separated with a straight line, the classical AI was the undisputed champ. No contest. It scored a massive 93.2% accuracy, while the quantum AI kind of stumbled. And honestly, this was totally expected. It just confirms that for simple, clear-cut stuff, the classical approach is still king. I mean, that is a huge 25.8% performance gap. It really proves that for simple problems, using a quantum computer is complete overkill. It's like using a spaceship just to go to the corner store.
But watch what happens when the puzzle gets harder. On this really tricky concentric circles problem, the quantum AI suddenly closes that gap. I mean, they're performing almost identically. The difference just, poof, it vanishes. And this is our first big clue. Complexity is where quantum really gets in the fight. And now for the main event, the real-world breast cancer diagnosis. Okay, the classical AI still takes the win with 88% accuracy, but look at that. The quantum AI is right on its tail, pulling in a really powerful 78.6%. That is not just a respectable performance, that's a huge leap. And this, right here, is the most crucial takeaway from this entire showdown. The quantum circuit performed dramatically better on the messy, complex, real-world medical data than it did on any of the clean, artificial puzzles they threw at it. This suggests we might be testing these systems all wrong, that our simple lab tests could be seriously underestimating what quantum AI is truly capable of.
So this really surprising outcome basically handed the researchers a brand new set of rules, a practical guide for how to actually get the most out of these emerging quantum systems.
Rule number 1, you have to speak the quantum computer's native language. Think of it this way. Angle encoding is like turning a simple dial for each piece of data you put in. It's direct, it's robust, and it worked beautifully. Amplitude encoding, on the other hand, is like trying to balance a bunch of different data points on the very tip of a needle. It's way more powerful in theory, but in this real-world test, it was just too fragile. It completely collapsed. Rule number 2 is all about architecture. You gotta build tall, not wide. Adding more processing layers, making the circuit deeper, gave them a massive 39.5% boost in performance. It was a game changer. But adding more quantum bits, or qubits, making the circuit wider, did almost nothing. For these kinds of problems, depth is king. So let's put this all together in a quick cheat sheet. First off, for simple, linear problems, just stick with classical AI. We saw it dominate. But for complex, messy, real-world stuff, like that cancer diagnosis, quantum is a serious contender. When you do go quantum, remember to use the right language. Angle encoding was the clear winner here. And focus your resources on building deep circuits with more layers, not wider ones. And finally, and this is so important, test it on real data, because our clean little artificial puzzles might be seriously holding it back.
You know, this research does more than just give us a winner. It gives us a map. It suggests that the most exciting places for quantum AI might not be in solving abstract math problems, but in untangling the incredible complexity of biology, of finance, and all kinds of other real-world challenges. So the question is no longer if quantum computers will be useful, but where.